Hello everyone, welcome back. In this lecture we're going to be discussing about a very important concept in VLSI, which is called antenna effect. Alright, so those who would like to get their hands dirty and would like to involve in VLSI physical design or layout design area, or want to get expertise in that area, developing layouts for integrated circuits, it is important to know uh, what is the antenna effect, because if you don't know, then you might develop a layout which has this problem of antenna. It is an unwanted effect and your circuit will not work. Good. So in simple sense, we can say that antenna effect is nothing but the plasma induced damage. Okay. Now, what do we mean by plasma induced damage? Nowadays, during the manufacturing process, we need to etch out the unwanted oxide layer from the wafer. And typical process is being used, which uses the plasma. Okay. Now we're not going to go in detail about how this plasma process works and all. The idea for this lecture is um, to get a concept of antenna effect and how we can avoid it during the design process. Okay. In simple sense, antenna are floating metal layers. Okay. So the metal layers which are not connected to either ground or either other metal layers, those are hanging metal layers. Okay. So those are antennas. So those who have been designing or writing, say, digital design circuits or writing codes for digital design circuits in Verilog or VHDL, you might have noticed that if you don't connect, okay, if you don't connect the output or input of a block, electronic design automation tools give you the warning that this pin is hanging. Okay, that precisely the warning is for the antenna. So think about, you have this block, okay, circuit A or circuit C, some pins, okay. These are connected. You may have other input pins. This is I1, I2, and you have another pin O1, and this O1 is getting connected to an input of inverter and so on, and another output pin is hanging. So your tool may give you the warning that okay, this pin is hanging, O2 pin is hanging. It might create an undesirable antenna effect in simple sense, or it just will keep on accumulating the charge. Okay. So these are basically floating metal layers. And this effect comes because of the way circuit is being manufactured. Which layers are getting affected? Poly and metal layers get affected because of antenna. And due to this antenna effect, a transistor can be permanently damaged. It will break out the transistor. Now let's see a typical MOSFET cross section. So you guys might be familiar with this diagram. This is nothing but a MOSFET cross-sectional layout. As you can see here, the source, drain, and gate. Okay, polysilicon layer forms this this gate. Okay, and this is substrate or silicon. How this works, how transistor works, you might want to watch another lecture on transistor working. But for this lecture, let's concentrate on antenna effect. Now, to know or to understand antenna effect in detail, we need to understand how the etching process or manufacturing process works. Now, this is the idea of these steps. What I'm going to be discussing now is to give you an overview about one manufacturing process. It is not exactly that the way manufacturing works, but depending upon the technology or depending upon who is the manufacturer, whether it's the TSMC, Taiwan Semiconductor Manufacturing, or IBM, or which foundry it is, they may have more detailed steps. But this is in general to get an overview about manufacturing process and what do we mean by etching. So we take a substrate, silicon substrate, and grow a oxide layer. Okay, or in other words, this whole wafer, and you grow oxide layer on the wafer. And after that, the second step is typically you put a mask on that layer, oxide layer. And what mask does that, the idea here is that you want to etch out this oxide. The place where you don't want to etch out the oxide, you put a mask. And the place where you want to take off the oxide, you don't put a mask. And simply the etching process. Typically, this is UV, ultraviolet rays, or different other process, depending upon which foundry is that. And after the etching, you can see that the oxide layer is being taken off from the substrate at a selected portion where your mask was not there. And after that, you grow another thin oxide layer. And this may be different than the previous oxide layer, where it's more to create a field oxide layer. Okay, and then put another mask because we want to etch out certain portions of this oxide layer. Okay, and why do we need to etch out those portions? Say for example, in this area, we want to implant polysilicon. Okay, so for that implantation, we want to etch out that portion of the oxide to implant the polysilicon. Okay, and after that, we have implanted the polysilicon layer. And we put another mask for creating or for etching out the oxide. Say this oxide, we want to etch out so that we can implant the M+ impurity or dopant in the substrate. Okay, same way here. And after another etching, we have taken off unwanted oxide here, and next we implant the impurity or dope with the N plus. Okay, and after putting contact holes and implanting metal and doing metal etching, we came up with the transistor or a structure. So detailed process for manufacturing is complex. I may not cover in this lecture because most of these steps are very detailed and technology specific. I may not have access to the specific foundries technology. But this information is a general information. What are the typical steps? You may find this information in textbook or in published articles. So as you can see here that we have done etching at a couple of places, okay, and a couple of times we did the etching. So think about that for some reason, okay, if the charge is accumulated here more, okay, the current will flow more, okay, through this metal, and this more current will go here and more current will go here. And for some reason, if here more metal, so you are basically increasing, you're basically developing more charge here, because what happens is this polysilicon and this gate structure, this acts as a capacitor. Capacitor is there to store the energy, all right, and there will be some leakage current, and if you have more charge accumulated, okay, on the surface of the gate here, so think about what will happen. More charge is accumulated, okay, too much potential, and there is no way for this charge to get out from here. It's floating, right? It's not connected anywhere, it's floating. So when this charge will not get out, it will just be here, and if more and more charge is accumulated, it will break down this gate, and that will be permanent damage. You cannot repair. Your circuit will not work. So in simple terms, that we can say that the charge builds up, or DC builds up on metal lines, which is nothing but the antenna during the etching process. Since gate acts as a capacitor, gate will break down if the potential on gate reaches beyond breakdown limit. Okay. Now, what is a breakdown limit? Those are technology specific questions. Okay. One needs to look into the technology data sheet and need to understand different other technology parameters. But remember, in simple form, that if too much charge is accumulated and there is no sink provided for that charge to go off from the gate, it will break down the gate capacitor. Simple as that. And once the gate is damaged, it cannot be repaired. And how to predict that whether there will be antenna effect in your circuit or not? Antenna ratio is typically being used to answer that question. And antenna ratio is nothing but the ratio of the total conductor area, which is contributing in making the antenna, and the total gate oxide area. So that's the antenna ratio. So if that ratio is higher, what it means that if the ratio is higher, antenna ratio is higher, means you have more conductor area. which is contributing for the antenna. And since this is not connected anywhere, so charge will accumulate, it will build up, build up, build up, and eventually it will break down the gate. So remember, higher the ratio, greater is the possibility of failure. Now there are different design rules in each technology, okay, to take care of this antenna. And those design rules, one has to specify in place and route tools specification or constraints, say magma constraints or synopsis constraints for antenna effect rules. Now what can we do? What can we do at design level when we are designing the circuits, so that there is very low possibility of antenna effect, or almost nil. So first of all, let's talk about the wire routing. Okay, so since we already know that the antenna effect is there in metal lines and polysilicon lines. So two kinds of wires getting affected, polysilicon and metal. And the idea here is to reduce the area. Okay, so how you can reduce the area? Width, most likely width you can't reduce, it's specific to technology as per design rules. You can play around with the length of the wire, okay, and also you can play around with the routing of the signal wires. So typically you route those signal wires to the top metal layers, and in that two kinds of scenario may happen. Let's talk about first scenario. Say your gate, okay, your gate is connected to diffusion area via metal line. Now here simply you have routed the signal wire to top metal layer M4. Okay, now in this scenario, see the distance of from the gate to the diffusion. You can think of this is the metal layer, which is pretty long, and it's going to be contributing more towards antenna effect. And now here its length is 150 lambda based design rules. This is for example. So it's not too long wire. M3 is short and it will not break the gate. So your circuit is good. Now whether 150 lambda is right or wrong, one needs to check with the technology. But here, to give an example, that your metal line M3 is short, so you are safe there. Okay. For each technology, there is a defined rule that you can have only this much long metal line. If you have longer than 150 lambda, say 2000 lambda, then it's too long. You might end up developing antenna effect in your circuit. So let's talk about scenario 2. Same way, you routed your signal line to top metal layer, but in that case your M3 level metal routing is too long, about 1500 lambda. It's just too long. So what's going to happen here? The total area of the metal or the conductor which is going to contribute to antenna effect will be more, and your antenna ratio will be higher than the breakdown limit. And this is dangerous. It's a danger. So you see where we are coming with that. We are dealing with the very long wires. Okay. Now 1500 lambda, I just gave an example, but that again one needs to check with the technology. Okay. What we can do to avoid such kind of situation. First of all, fundamental rule is that break the long wires. And where to break the long wires? Always remember, break the long wires near the gate, because which element is gonna be affected by the antenna? It is your gate, which will get breakdown because of antenna effect. So overall idea is to reduce the area of the conductor which is contributing to the antenna getting built up at the gate. Okay, so break the long wires. And how to break? A technique called insert jumpers. Okay, insert jumpers near the gate. And jumpers are nothing but the metal connections. Break the wire and connect at some other layer via the contacts. So in our example, we can visualize it in a simple way. That here, this is the red color rectangle is jumper. So what we did here, we simply break this whole M3 long wire into two pieces and connect it, okay, these two pieces at a higher metal layer via the jumper. Okay, so this is a contact, and connected via jumper at a higher metal layer or a higher layer, may not be metal, and depending upon at which layer you are. So idea is simply to break the long wire. Okay, what else can we do? What else can we do? This we have seen that this is a long wire. We have to do something with that. So first solution, we saw that okay, we break it and put the jumper. Okay, now when we put the jumper, then we might end up in problems of that circuit is not routable anymore, because you see you are creating a leg, okay, dog leg, because you are creating a jumper here. You are breaking the wire and connecting a different layer, so you are basically making a dog leg here. And dog legs, if you guys know a little bit about routing, these create problems during the routing. The second solution is to insert diode near gate, so that whatever is the extra charge built up, okay, that can be sucked by the diode. Okay, so extra charge build up will get routed to ground via diode, or in other words, diode will suck up the extra charge, so your gate will not get affected via that extra charge and will be safe. So how we can do that? Very simply, put a diode near the gate. So when you put a diode near the gate, so whatever charge, extra charge is built up on this line here is getting the path to sink, and it will not be accumulated here. Okay, remember that whatever solution we are gonna do, either diode insertion or either putting jumper, it has to be near the gate which is getting affected by the antenna effect. All right, all good. Now let's talk about general design rules. As I said earlier, different technologies have different design rules. So you might have to check with the technology team or get the different manufacturing companies or vendors data sheet. Typical antenna rule is basically antenna area divided by gate area should be less than maximum antenna ratio. It's a typical, in general, antenna rule. One can say that. All right. So thank you very much, guys, for listening. I hope you guys are enjoying lectures on LeProFesseur. If you are struggling with certain concept, or if you need lectures on other topics, feel free to send me a message. I appreciate your feedback, your wonderful comments, and thank you for subscribing. Those who have not subscribed, please do subscribe. We appreciate your feedback and support.